In this video, we'll be doing a AP Physics 1 Unit 7 Oscillations FRQ. So a simple pendulum consists of a light string of L with a small ball of mass m attached to its free end, placed on a perfectly horizontal tabletop. A bullet of mass m travels horizontally toward the ball at a speed of v and collides with the ball perfectly inelastically. The combined mass of the ball and the bullet move along a circular arc with the string length as the radius and the fixed top end of the string as a center, performing a simple harmonic motion. So we're asked what is the initial speed of the combined mass ball plus the bullet immediately after the collision. So our setup is going to look like this. Right now, just look at the, up here, this is the ceiling, this is the wall, and this is the string. So the ball is hit by the bullet, and then it will swing back and forth. So in order to do part A, we have to remember that in this scenario, we are going to have a loss of energy, so then we cannot use conservation of energy in our system. So that's because we have perfectly So because our collision time is going to be negligible, our external impulse that is going to be exerted in the collision is going to be negligible in the tangential direction. So that means we have linear momentum conserved because this is a perfectly inelastic collision. So we know that before the collision, initially, we have the bullet momentum, which is equal to small m, large V. And we know that the ball is going to be at rest. So that means that the momentum is going to be equal to 0. So we know that after the collision, we're going to have a combined mass, which is going to be m plus big M. And then we know we have a common speed, which we're going to call v2. So if we have m and v here, we are going to have that equal to the combined mass of big M plus small m, v2. And then if we solve for v2, that is going to be equal to the common speed. Now for part 2, we're asked to derive to calculate the mechanical energy that was lost during our collision. So in order to do this, we know that our mechanical energy is going to be our loss, and this is going to be equal to the kinetic energy that we had beforehand, and we're going to subtract it from the kinetic energy that we had afterwards. So we know that in the beginning we had 1/2 mv squared because only the bullet was moving. And then we have, after the collision, so let's actually just do K initial minus KF. KF is going to be 1/2 m plus m v2 squared. So we're going to substitute in the fact that v2 is equal to m times v over m plus m. So we're going to have that Kf is equal to 1/2 m plus small m plus v, or m times v, m plus m squared. And then this is going to simplify to 1/2 m plus m squared v squared divided by m plus m squared. So this is equal to 1/2 m squared v squared over m plus m. So now we have Kf. We just substitute this in and subtract this from 1/2 mv squared to find our E lost. So what we can do is we can factor out our 1/2 mv squared. So we're going to have 1/2 mv squared out here, subtracted 1/2 m squared v squared over m plus m. So this is going to be 1 minus m plus m. So we can put this over a common denominator. For our 1 minus 1 m squared, or actually, this is just going to be m. We can write this as m plus m minus m over m plus m, because this is equal to 1. So after this would be m plus m. So this is 1/2 mv squared times m plus m. So the energy that is lost is 1/2 mmv squared over m plus small m. Now, for part 3, we're asked to derive the expression for the period of a simple harmonic motion of the combined mass. So we know that when we have period in pendulums, it's going to be 2 pi the root of L over G, this length of G. So our period does not depend on mass. So even though we went from m to m plus m, the period is going to be the same. It only depends on length and gravity, not the mass that is attached. For B1, we're asked, what is the maximum angular displacement of the combined mass after the collision? So we know that after the collision, the combined mass has a speed of m, v, m plus m. Then it's going to swing up, and then the kinetic energy will turn into gravitational potential energy. So here, when the ball is going to swing up, we're going to have, at this point, your E is going to all be kinetic energy. But when you're at the bottom over here, your energy is going to only be, or up here, your energy is gravitational potential energy. And then here you have your energy is kinetic energy. And your potential energy is equal to 0. Up here, your potential energy is going to be at its max, and your speed is equal to 0. So we can write conservation of energy for part B1. So we're going to let theta max be our max angle. So we know that in this scenario, we're going to have the length of the string as L, and that's your hypotenuse. So because that's our string, we want to find what this change in height is, and also this adjacent side of this triangle is. So we're going to cut a perpendicular here, and that creates a right triangle. When we have a right triangle, we can use our trig. So we can relate theta with the sides by using adjacent and hypotenuse, which is equal to the string. So over here, we have cosine theta is equal to the adjacent side divided by the hypotenuse. The adjacent side is basically the max vertical height from the distance to the pivot when the ball is at its highest point. So that's why we say cosine theta is equal to that divided by L, because L is our hypotenuse. So if we want to isolate what that height is, that adjacent side, then we're going to multiply both sides by L, and then that L will cancel out. So we'll get our adjacent side is equal to L cosine of theta. So if we want to find the change in height, we know the change in height is equal to our hypotenuse minus that L cosine theta, which was our adjacent side, because our entire string subtracted by that adjacent side is going to equal to that little difference that the height is of the ball that is going to travel when it goes up in that circular arc motion. So then we can replace hypotenuse with our length minus L cosine of theta, and then we get this from factoring out our L. So we know that our total length of a string is equal to the change in height plus L cosine of theta, just to check our work. So now we can use we can write our conservation of energy. We know that H, which is our vertical rise of the pendulum bob from the bottom, this will equal to L1 minus cosine of theta max. So if we write our equation, our initial energy and our final energy, we're going to have 1/2 m plus m v2 squared is equal to m plus m gh, because we have UG up here, and then we have kinetic energy down there. So this was at the bottom, and then this is at our top. So after this, what we can do is we can substitute in our h. Our h is this expression, and our h is right there. So what we're going to have is 1/2 m plus m v2 squared is equal to m plus small m gl 1 minus cosine of theta max. So we have a m plus m and m plus m here, so we can actually cancel that out. And this will equal to 1/2 v2 squared and gl 1 minus cosine theta max. Now we want to solve for cosine theta max. So what we're going to do is we have 1 minus cosine theta max on this side, and we have 1 over 2g, the length, m big V, large M plus small m squared. So if we want just cosine theta max, now we can just move cosine theta max here, and then we have 1 on that other side. We just add 1 to the other side and then subtract everything on that side. So we have minus 1 over 2 GL, and this is MV, M plus M squared. So now to get theta max, all we're going to do is take the inverse cosine of both sides. So theta max is equal to 1 minus 1 over 2 g times the length, mv, m plus m squared. So this is our answer. Now we have that simple harmonic motion occurs when the restoring force is directly proportional to the linear displacement of the oscillating object. When the angular displacement exceeds 5 degrees, the restoring force is no longer linearly proportional to the linear displacement. Determine the maximum ratio of the bullet's mass to the ball's mass for the combined mass to undergo simple harmonic motion, i.e. for the maximum angular displacement to be at most 5 degrees. So we're finding the max ratio, m over m, where our theta max is going to be less than or equal to 5 degrees. So if we want our simple harmonic motion to be valid, the max angle has to be at most 5 degrees. So we're going to set our theta max equal to 5 degrees. So from part B, we already have that 1/2 mv over m plus m squared is equal to gl 1 minus cosine 5 degrees. Here, you're going to multiply both sides by 2. We have mv, m plus m squared is equal to 2 gl 1 minus cosine 5 degrees. After this, just take the square root of both sides. We have mv, and then you're going to get the root of 2gl 1 minus cosine 5 degrees. After this, we're going to let that V max is equal to the root of 2gl 1 minus cosine 5 degrees. Then we're going to have that mv, m plus m is equal to V max, because that's what we have for our V. So now we're going to use this to solve for the ratio that is going to be m, small m, over m. So we know that mv is equal to V max m plus m if we just multiply both sides. So then we're going to distribute here. So after we distribute that, we have mv is equal to v max m plus v max m. So we're going to move these terms with the lowercase m together. So we have m v minus v max m is equal to v max big M. Then we can factor out this m here. Then we can divide by v minus v max. And then we can substitute back in for our v max. So we have m over m is equal to the root of 2gl, 1 minus cosine of 5 degrees, divided by v minus the root of 2gl, 1 minus cosine of 5 degrees. So that's our maximum allowed ratio. Now, optionally, if we had a small angle, when you have very small angles in radians, you're going to have 1 minus cosine of theta is approximately equal to theta squared over 2. So if we have theta is equal to 5 degrees in radians, then we're going to have theta is equal to 5 pi over 180 degrees, which is pi over 36. So when we have 2gl, 1 minus cosine 5 degrees, that's going to be approximately 2gl theta squared over 2, which is equal to gl theta squared, because that 2 is going to cancel out. So v max is equal to theta, the root of gl. So m divided by big M max is going to be approximately pi over 36, root of gl, v minus pi over 36 times the root of gl.